Good morning. Just looking at what we have been working with, um, and we have been dealing with systems of equations, both linear and nonlinear, and just momentarily going back to linear systems. Okay, we have for this particular system, again, we're looking at solving for x and y. And now for this arrangement, we have one of the variables to be isolated. Okay, and we're looking at the values of x and y that will satisfy both y is equal to 4x plus 3 and x plus y is equal to 13. And let's say that in terms of the setup on this one. And again, there are varieties of approaches you can take in order to solve for x and y, but you could arrange things where you could still utilize the method of addition. Okay, let's say that with another approach. Okay, we have from the first equation, okay, we have y to be isolated, and an alternate approach you can take is that we have what is referred to as the method of substitution. Okay, and for what we have in the case of this approach, okay, so we have with the method of substitution, okay, again, we have y to be isolated in the first equation, and with the substitution, okay, like y is isolated, and that which is isolated we can go ahead and substitute for in the second equation. Okay, so what I mean here is that you got y is equal to 4x plus 3, and I can take this 4x plus 3 into the other equation and have that to represent y, so that I can go ahead and create a pathway to solving for x. Okay, so here I can just substitute for y and solve for x. And we have with this particular approach, okay, so we're going to have x plus, and again, changing the y. Okay, so have the quantity of 4x plus 3. Again, we have is equal to 13. Okay, and upon removing the parentheses, okay, and there will be no sign change since we do not have subtraction in any of the operations. Okay, so we now have x plus 4x plus 3 is equal to 13, and then combining the variable terms, so we have that 5x plus 3 is equal to 13, and now we have a two-step linear equation. Okay, and if I look at taking 3 away from both sides, okay, so we got 5x is equal to 10, and we have with division by 5, okay, so we're going to have the x is equal to 2, okay, and so we have half of the solution with x determined, and we have in terms of following through, okay, so I can plug 2 in for x in either equation, okay, and solve for y, and I can take either one. It could be like plugging in 2 for x and x plus y is equal to 13, or 2 for x and y is equal to 4x plus 3. And so either equation will work. And so we have in this situation, okay, so I can plug in 2 for x, solve for y. And we have in following through, okay, so we have that y is equal to 4 times 2 plus 3. And 4 times 2 is 8 plus 3. So the value of y in this case will be 11. Okay. And so you have x at 2, y at 11, and you can always go back and check. So with x at 2 and y at 11, so you have 4 times 2 is 8 plus 3 is 11, which we have for y. And again, we have 2 plus 11 is equal to 13. Okay, so those values will check out. And we thus have our solution. Okay, so you have x is equal to 2. And y is equal to 11. And I know that in Alex, okay, likes to put the solutions in terms of ordered pairs. Okay, so we have putting in terms of a point in the xy coordinate system. Okay, so you have xy is equal to 11. Okay, and we also have in the case working with systems of equations. Okay, and let's say that it's going back to what we had from the second part, okay, of the test 4 review study guide, and I had numbers 14 and 15 left over. And from what we had here, okay, we had a system of equations. And for what was in number 14, okay, we had in this one case, you had 2x minus 3y, okay, is equal to 7. And also we have 4x plus 2y is equal to 26. Okay, and if you notice, we have in this system, okay, we don't have additive inverses between what is assigned for x or y. Okay, so you have 2x and 4x, and we have negative 3y as well as 2y, and we can adjust either one equation or both equations, where one variable can be eliminated and the other to be solved for from the start. One approach is that I can make the 2x into a negative 4x by multiplying the first equation by negative 2, and I could go ahead and solve for y. But I think what I'll do in this particular case is that I'm just going to eliminate y and solve for x first. So we have the y terms. Okay, so you have you have negative 3y, and the coefficient negative 3 has an absolute value of 3, and we got 2y with an absolute value of 2. So you got the absolute values of 2 and 3, and the smallest multiple of both 2 and 3, the smallest number that both 2 and 3 will go into, is 6. So if I raise the y terms, okay, where the coefficients will have an absolute value of 6, I can make the 2y into a 6y, and with a negative 3y, I can create an additive inverse by adjusting that, making this into a negative 6y. So what I can do here is that in the case of the simultaneous operations, and that is to adjust both of these equations. So if I make the negative 3y into a negative 6y, I can just multiply by 2. And for 4x plus 2y is equal to 26. Okay, so I make the 2y into a 6y if I multiply that equation by 3. So in looking at adjusting both equations, okay, so you got 2 times the first equation, so we have 4x minus 6y is equal to 14, and for 3 over 4x, okay, so this is going to be 12x, and 3 over 2y, okay, that is going to be a 6y, and 3 over 26, okay, so that is going to be 78. Okay, so I now have additive inverses with negative and positive 6y. And so for what we have left, okay, so you have 4x plus 12x. So this will make 16x. Once again, the y terms cancel. 14 plus 78 Okay, this will be 92. Okay. And looking at what we have and following through, again we have 16x is equal to 92. And if I get this equation in terms of x equals, okay, we have division by 16. So right now I have x is equal to 92 over 16. And this ratio can be reduced, okay, not to an integer, but a number that I can either leave in fractional form or as a terminating decimal. Okay, so we can say that x is equal to 23/4, or if I were to write as a decimal, okay, this is going to be at 5.75. And in terms of taking what we have in solving for y, and I can again plug in, say, 23/4 or 5.75 for x in either of these equations and create the pathway to solving for y. And since I have a positive y term in the second equation, I will use this one in creating the pathway to solving for y. Okay. Okay, so I have 4x plus 2y is equal to 26. Okay, so just taking what we have here. Okay, so plug in either form, decimal or fraction, for x. And solve for y. Okay. And okay, so if I plug in the fraction or the decimal, okay, you're going to have, if I have with the fraction, you're going to have the 4's to cancel. Okay, then we have plus 2y is equal to 26. Okay, so 4 times 23/4, okay, that is going to be 23. And we have plus 2y, okay, is equal to 26. And for what we have in terms of following through, okay, so if I take 23 away from both sides, so I'm going to have that 2y is equal to 3. And we have a division by 2. Okay, so we're going to have like x, y is going to be a non-integer. So I can say that y is equal to 3/2 or 1.5. And now in the case of what we have, okay, for the solution, again, you can use either fraction or decimal. Okay, so again we have x equal to 5.75. And y is equal to 1.5. Okay. You can also once again express in ordered pair terms. We're going to have 5.75 and 1.5. And again, this is one approach you can take in order to solve for the system. And as mentioned earlier, I could have eliminated the x terms and solve for y, but I did it the other way around. Okay, so there's more than one way of using or creating a pathway to using the method of addition, where I could have eliminated x and solved for y first and then solved for x. All right, now for what we have in the case of number 15, okay, now we have a system of non-linear equations, and for what we have in this one, Okay, we got x squared plus y squared, okay, is equal to 25. And we have also x squared minus y squared, okay, is equal to 7. And if you notice, okay, we already have an additive inverse relation, okay, between the y terms, okay, and we have positive y squared in the first equation and a negative in the second, okay, and so we can just go ahead and cancel out the y terms. So upon adding the equations together, we have x squared plus x squared, so this will make 2x squared, and we have 25 plus 7, okay, will come out to 32. And looking at narrowing things down, okay, so we got 2x squared is equal to 32, and to get this in terms of at least x squared, we can divide what we have here by 2. So we're going to have the x squared is equal to 16. Okay, so you have x squared is equal to 16. Now there are two values in x whose square will be at 16. And you can perform either the translation of this equation into standard form, like x squared minus 16 is equal to 0, and factor, and then use the zero product property to get to the values in x. Or I can use the square root property of equality. Okay, so with this approach, if I go from x squared to x, we'll have the x is equal to plus or minus, okay, the square root of 16 and so we're going to have the x is equal to plus or minus 4. Okay, now in the case of y squared, okay, for this one, okay, so the equations have both x squared and y squared. So what I can do in sort of creating a relatively quick pathway to solving for y, and just choosing either equation to work with, I'll go with the first. So I have x squared plus y squared is equal to 25. And what I'm doing here is I can just plug in 16 for all of x squared, not just x, but all of x squared. And then we have with the following steps, okay, we'll create the route, okay, to solving for y. Okay, so plugging in 16 for x squared. Okay, so I have 16 plus y squared, okay, is equal to 25. And then looking at taking 16 away from both sides, and so we're going to have that y squared, okay, is equal to 9. And going from y squared to y, so you have y is equal to plus or minus, okay, the square root of 9. And so we have that y is equal to plus or minus 3. Okay, so we have combinations, not just one solution, but combinations of solutions. Okay, so you have just like in shorthand, okay, you have x is equal to plus or minus 4. And y is equal to plus or minus 3. And just laying out the coordinates, okay, the ordered pairs. So one combination is where you have both x and y to be positive. Two combinations where one is positive and the other is negative. So we have like 4 and negative 3. as well as -4 and 3. And we have the last combination where both of these equations will ring true will be where we have both x and y to be negative, where we have -4 and -3. All right, and some other things that we have regarding systems of equations. Now, we've looked at separating the linear systems apart from any nonlinear systems. And let's say that if you have a bit of a combination of both, where we have a system of equations where one equation is linear and the other is nonlinear. And this one's going to be a little bit tedious. And say if we look at solving for x and y, and we'll say that in this system, okay, we'll have x plus y is equal to 14. And also we're looking at those values of x and y not only where they will add up to 14, but where the sum of their squares will amount to 100. Okay, and so we have in this particular setup, you can see you have a linear equation. Okay, we have with x plus y is equal to 14. And again, we have a nonlinear, okay, where we have the sum of the squares of x and y to be at 100. Okay, and in this one, now when I resumed with the system of equations, okay, I had introduced, okay, the method of substitution. Okay, and I'm going to do likewise, okay, for what I have in this example. Okay, so I can write the first equation either in terms of x equals or y equals. And what I'm going to do here is that for x plus y is equal to 14, and since we had a history of looking at the slope-intercept form of an equation, we've probably been a bit more accustomed to isolating y as opposed to x. Okay, and I'm just going to do that here. Okay, so we can say that we have y is equal to -x plus 14. Okay, so we have y in terms of x, and I'm going to translate this second equation in terms of the variable x. Okay, and now, so if I take the y here, so we plug in -x plus 14 for y, not y squared, but y. And be able to initiate the process of solving for x. Okay, and so for what we're going to have here, we got x squared plus what is going to be the square of -x plus 14. And we have is equal to 100. Okay, and I'm just kind of moving to the side here. Okay, now for the square of -x plus 14. So we're looking at -x plus 14 times itself. And -x times -x, so this will be x squared. And we have the outside and inside products. Okay, we have that -14x for each. -14x minus 14x, so -28x. And we have 14 times 14 is going to be 196. Okay, so we have some high absolute value coefficients in the mix. Okay, so just taking what we have here, and so we have for the rewrite. Okay, so we've got x squared. Again, for the square of negative x plus 14, so I have x squared minus 28x plus 196 is equal to 0, and then just combining the square terms in x. So I have 2x squared minus 28x plus 196, and that should be equal to 100. It is eventually going to be equal to 0, but okay, so 2x squared minus 28x plus 196 is equal to 100. Okay, so just putting this equation in standard form. Okay, so I can take 100 away from both sides. So we have 2x squared minus 28x plus 96 is equal to 0. And say if I divide the equation by 2, notice we have even valued coefficients throughout. Okay. So with division by 2, so we have x squared minus 14x plus 48 is equal to 0. And we have with the factoring, okay, so we have, when factoring, we'll have x minus 6, and the other we will have with x minus 8. And we have with the 0 product property. Okay, so if we have x minus 6 equal to 0, we have the x is equal to 6. And for x minus 8 equal to 0, okay, so I had the x is equal to 8. Okay, and let me mention, okay, so I had a first order equation and also an equation second order in both x and y. So if you have different degrees between the equations, here's just a rule of thumb. Always plug in into the simplest or lowest degree equation. Okay. Notice we got both of these values are for x. Okay. And so for what we have here, okay, so again we have x is equal to 6. We have also x is equal to 8. And just stressing this statement here. Okay. So between these two equations in the original system, okay, obviously x plus y equals 14 is going to be the lower degree equation. And so we have just filling in. Okay, so x is equal to 6. Plug in here. X is equal to 8. Plug in. Again, for x, and there's going to be a bit of a swap, okay, between the x and the y values in the outcomes. Okay, so you have, if x is 6, we're going to have 6 plus y is equal to 14, and from this we're going to have that y is equal to 8, and if x is equal to 8, well, x plus y equals 14 becomes 8 plus y is equal to 14, and guess what? We had that y is equal to 6, and so it's going to follow that for the solution, we'll end up with switched values for x and y. Okay, so the solution, okay, we have in one capacity we have the xy is equal to 6, 8. So we have, with reversing the order of the coordinates, we also have xy is equal to 8, 6. Okay, and you could always go back and check. Okay, so regardless of whether x is 6 or 8 and y is the other value, the addition or the sum is going to come out to 14. And again, have 6 squared plus 8 squared, or 8 squared plus 6 squared will come out to adding 64 and 36, where we have 100 as the outcome. Okay, so those can be your possible values for x and y. We have 6, 8 in the order pair, or possibly 8, 6. Now, just one thing to mention about systems of equations. And this is going to cross over into descriptions or categories. And for what we have in the case of equation systems, I'll just call this classifying equation systems. Okay, now we'll say now the ones we've been looking at so far will fall into this first category, and we have for a system with a finite number of solutions. Like you have one solution or two solutions. Like the last equation, we had technically two solutions. Okay, so a system with a finite number of solutions is going to be regarded as consistent and independent. Okay, so again, we have for the system. Okay, so this is going to be consistent and independent. Okay. Now we have with the next type of system. We have for a system with no solution. Is going to be regarded as inconsistent. And we have, in the case of the third category, so we have a system with not a finite, but with an infinite number of solutions. Okay, this one is going to be regarded as consistent and dependent. Okay, so you have three types of systems, or three categories of equations, and it's kind of just a quick run through. If I'm looking at determining the type of system for the following, okay, and we have, let's say we have a system of equations. Okay, say we have that x plus y is equal to 7. And let's say we have negative x minus y is equal to 10. Okay. Okay. And if you notice, we have additive inverses with the x and the y terms. Okay, so if I were to add the equations, okay, so you have with x plus y equal to 7 and negative x minus y equals 10. Okay, so for what we're going to have here, okay, so we're going to have the x's are going to cancel, the y's are going to cancel, and we have 7 plus 10 is 17. And guess what? Left hand side, okay, we got x and y to cancel, so the left hand side is going to be 0, while the right hand side, okay, is going to be at 17. So we're down to a false equality statement. So that means that there is no solution for x and y. And guess what? So for what we're going to have in consequence, a system that has no solution is going to be inconsistent. Okay, so this first case, okay, is going to be inconsistent. Now, let's say that if I have, for the next one, okay, so if I have that x plus y is equal to 7, and I have the x minus y is equal to 1, okay. So I still have additive inverses in the mix, and this time exclusively with the y terms. So I have to look at adding the equations. So we have for x plus y is equal to 7, and x minus y, okay, is equal to 1. Okay, so for what I have in x, you have x plus x will make 2x. The y's will go out. And so we have that 2x is equal to 8. Yes. Okay, so you have for division by 2, okay, so we have the x is equal to 4, and you can go back and plug in 4 for x in either equation. So you have 4 plus y is equal to 7, and so we're going to have that y is equal to 3. Okay, so this equation, okay, we're going to have for the solution, okay, we have one solution, so you have a finite number of solutions. Okay, so you have for x, y, so you have x at 4 and y is at 3. Okay, so that is the only solution, and a system with a finite number of solutions, okay, is going to be consistent and independent. So this is the type of system we're going to have in this case. Okay, so this equation, okay, so that is going to be consistent and independent. All right. Okay, now for what we have in the third case. All right, see we have and really I'm throwing this in, okay, just like for Alex, there's a bit of ambiguity, like from Alex, at least in terms of what the answer is expected to be. Okay, now in terms of the type of system, okay, that's a bit of a shoe-in. But let's say that for this system, okay, so if I have that x plus 2y is equal to 7, and I have also that negative 2x minus 4y is equal to negative 14. Okay, and if I take what I have here, okay, so I don't have additive inverses yet. But I can make a very quick adjustment. Okay. So we have with the equations, okay, if you notice, okay, we have negative 2x and negative 4y, and their respective additive inverses would be 2x and 4y. And guess what? I can get to their additive inverses simultaneously by just simply taking double the first equation. So I have that 2x plus 4y is equal to 14, and then just rewriting the second equation. So I have negative 2x minus 4y is equal to negative 14. So you got 2x minus 2x is 0. 4x minus 4y is also 0. And we got 14 and negative 14 is 0. And guess what? Both sides are equal. And this statement, okay, is going to be true. Okay. And now, for what you have in the case of the solution, okay, now, something like Alex would say that this type of system, okay, is going to have an infinite number of solutions. And you could technically say that both x and y will be the set of all real numbers. Okay, but in terms of the layout for y itself, okay, it wants the solution in y to be what we have in terms of x. Okay, so I can take either equation because there are two different ways of saying the same thing in terms of what we have for x and y. So if I go back to the first equation and I write y in terms of x, okay, so I have x plus 2y is equal to 7. And I take x away from both sides. Okay, so we have that 2y is equal to negative x plus 7, and then we have a division by 2. You can either itemize the terms or just leave in compact form, whereupon we have y is equal to negative x plus 7 all over 2. And again, so we have for the solution, okay, we say that x will be the set of all real numbers. But for what we have in the case of y, okay, so for any value I plug in for x, now what I must have in y, to put it in terms of x, then we have negative x plus 7 all over 2. So this system has an infinite number of solutions, and a system with an infinite number of solutions is going to be regarded as consistent and dependent. So again, there are an infinite number of solutions. Okay, and now I wanted to throw that in because I know that sometimes, you know, there's a lot of stuff that is in sync between what's in the textbook and what is in Alex, and sometimes Alex can just ask some things that, you know, just not readily, for lack of a better phrasing, just not readily obvious or spelled out quite so much in the case of what is in the textbook. So I thought I would just throw this item in. Okay, now for what we have in for this test 4 review handout, and just going back to what we have with logarithmic expressions. Okay, and this one, okay, we have a lot of similar stuff, but some items with a little bit of an added twist. Okay, it looks like for at least for the first 2 problems, okay, you're looking at a situation where it looks like we'll be using the property, our first logarithmic property, where you have the base A logarithm of a to the x is equal to x. And for what we have in the case of the first question, okay, so we're looking at the base 6 logarithm of 6. If I look at determining what the final result is going to be, so you had the base 6 logarithm of 6, and so if you notice we have like base A logarithm of A had the base 6 logarithm of 6. So your A value is going to be at 6, and in terms of the x value, you don't have raised power for the exponential base 6, but you'll read this as if it had been 6 to the first power. So the base 6 logarithm of 6 is going to come out equal to 1. And for what we have in the case of the second item, and we have the base 4 logarithm of 1 over 64 . Okay, now for 1 over 64, now 64 is both a multiple and an integer power of 4. Okay, so you've got 64 is going to be 4 to the third. Now, 1/64 is going to be the reciprocal of 4 to the third. And if I rewrite 1 over 4 cubed in terms of a direct exponential base 4, okay, so you have the base 4 logarithm of 4 to the negative 3. Okay, so you have the base A logarithm of A to the x formation. And so that x value, okay, that is going to be negative 3. Now, for what we have in the case of the next item, okay, so you have the base 5 logarithm of 25 to determine. Okay, so you have it in this one. Okay, so you have the base 5 logarithm of 25, and 25, okay, that one you have to be both a multiple and an integer power of 5, and 25 is going to be 5 to the second. So the base 5 log of 5 to the second, okay, that is going to go to 2. And for the base 2 logarithm of 1 over 32, okay, so you have a reciprocal of a power of 2. Okay, so you got 1 over 32. Now 32 would be 2 to the 5th power. And so here we have the base 2 logarithm, and the reciprocal of 2 to the 5th is going to be 2 to the negative 5. So back to the base A log of A to the x, and the missing value in this case is going to be at negative 5. Right. Now, and looking at what we have for the next set of items, and again we have for evaluating expressions. Okay, so we have base A logarithm of 1/8. Okay, so this would be like base 8 logarithm of 1 over 8 to the first. And just rewriting 1/8 directly in base 8 terms. So 1 over 8 is going to be 8 to the negative 1. So you got the base 8 logarithm of 8 to the negative 1. So the base 8 logarithm of 1/8, okay, this will come out to negative 1. And for what we have in the case of the base 3 logarithm of 81, okay, so 81, okay, is a multiple of 3, and also an integer power of 3. Okay, so with 3, you got 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is 81. So it would take 4 3s to attain a product of 81. And so we have with base 3 log of 3 to the 4th. Okay, and so that output, again, we have at 4. Alright, now for what we have in the case of the next item, okay, and okay, there's a little bit of a twist on these, especially with parts B and C. Now we have with A, okay, so you got sum of base 9 logarithmic terms, and I'm looking at making it to a single base 9 logarithm. So from part A, so I have the base 9 logarithm of 7 plus the base 9 logarithm of 10, and looking at piecing together, again, addition is going to imply multiplication of the attachments. So we have a base 9 logarithm of 7 times 10, and so we'll come out to a base 9 logarithm of 70. Okay, so 70 is going to be the missing value in this problem. Okay, now for what we have in the case of part B, okay, you could look at this from either two perspectives. Okay, now I'll just move over here. Okay, so you have for part B, we'll say that X will be the missing value. And for the setup, okay, so I can say that I can say I have a base 4 logarithm of X minus the base 4 logarithm of 5 is equal to the base 4 logarithm of 3/5. Okay, what I mean by this, I can either combine these logarithmic terms together into a single logarithm, or I can expand what is on the right. Okay, but regardless of whatever I have, okay, X must be positive. Okay, so you either combine on the left or expand on the right. Now, so I'm just going to expand on the right. So here we're going to have the base 4 logarithm of X minus the base 4 logarithm of 5, okay, is equal to the base 4 logarithm of 3 minus the base 4 logarithm of 5. Okay, and if you notice, we have identical logarithmic terms on both sides. So if I were to add the base 4 logarithm of 5 on both sides, so we have these terms would cancel. So I have the base 4 logarithm of X is equal to the base 4 logarithm of 3. And if you notice, I have single terms, just like before with exponential equations with a like base. If I had single terms and the same exponential base on both sides, I could set the powers equal to each other. Well, here we have individual logarithmic terms in the same base, and I can go ahead and set the attachments equal to each other. And so it's going to follow for the missing value. Okay, we're going to have X equal to 3, so X will be the result for what we have in the case of part B. Okay. And for what we have for part C, okay, so you have a base 6 logarithm of 25, And if I rewrite this in terms of base 6 logarithm of 5, okay, so I have a base 6 logarithm of 25. And if I write in terms of where 5 is going to be the attachment, so 25, again, we have both a multiple and an integer power of 5. So 25 is going to be 5 raised to the second. Okay, and again, looks like we're going to be looking at converting powers into coefficients. So the base 6 logarithm of 25, okay, this will become 2 times the base 6 logarithm of 5. Okay, and then we have for the next item, and we have in question number 5. Okay, it says to use the properties of logarithms to expand log, or the base 10 logarithm of z times y to the 9th, and it says should not have any exponents and assume that all variables are positive. Okay, so we have, looking upon this particular term, okay, so I have log of z times y to the 9th. Okay, and looking at expanding, okay, so we have in the attachments, okay, have the operation of multiplication, and multiplying is going to imply addition when writing and expanding out into separate logarithmic terms. Okay, so we'll have the base 10 logarithm of z, and we have plus the base 10 logarithm of y to the 9th. Okay, and again, I have an exponent with 9, and I just convert this into a coefficient. So this will come out to the base 10 logarithm of z plus 9 times the base 10 logarithm of y. All right. Now for what we have in the case of number 6, now this one, kind of a different one, with its own special twist. So we have another base 10 logarithmic term, and we have z to the 3rd, and we have all over the square root of x to the 5th times y. And say if I look at writing in terms of non-integer powers, what we have in the radical, okay, so I have base 10 logarithm of z to the 3rd. I'm just going to mention now, if you notice in the denominator, okay, so I have the square root of x to the 5th times y. Okay, and whenever you're dealing with the square root, you're dealing with 1/2 in terms of an exponent. Okay, so you have the square root of all of x to the 5th y will be the same as taking x to the 5th times y and raising to the 1/2, and the 1/2 degree is going to affect both x to the 5th as well as y. So we're going to have in the expanding, we have like x to the 5th, its own factor is going to be taken to the 1/2 degree. And guess what? We have with y, that is also to the 1/2 power. And we have with the power property of exponents. Okay, so this will come out to x to the 5/2 times y to the 1/2 power. So just mention here. Okay, so in the rewrite, so I'm going to have the base 10 logarithm of z cubed, and this is going to be all over x to the 5 halves times y to the 1/2 and so just looking at expanding. Okay, so I have at the top, so I have base 10 logarithm of z to the 3rd, and with both the x and the y factors in the denominator, okay, each of their own respective base 10 logarithmic terms will be negative. So we have minus the base 10 logarithm of x to the 5 halves, and we're going to have minus the base 10 logarithm of y to the 5 halves, y to the 1/2. And just looking at, once again, converting from powers to coefficients. And so we're going to have 3 times the base 10 logarithm of z minus, we have 5 halves of the base 10 logarithm of x minus 1/2 of the base 10 logarithm of y. Okay, so that one, a little bit of a tricky one, especially with the clustering of terms inside the radical, but still solvable and expandable. Now, for what we have in the case of item number 7, okay, so we have another expansion case. You have base 10 logarithm so you have 6 times, okay, the square of x plus 5 we have all over the cubic roots of x to the 4th and again, just taking what we have in the radical. Okay. If I rewrite, so I have the cubic root of x to the 4th. Okay, so this will just go to x to the 4/3. So I got the base 10 logarithm. Okay, so I have 6 times, again, the quantity of x plus 5 raised to the 2nd, and this will be all over x to the 4/3. And looking at separating, okay, so I got 2 factors in the numerator, and if I look at those first, okay, so we're going to have a couple of positive base 10 logarithmic terms. So I have that of 6, and we have plus base 10 logarithm of x plus 5 raised to the 2nd. Then I'm going to have minus, okay, the base 10 logarithm of x to the 4/3. Okay, now in terms of the individual term, where we had the base 10 logarithm of 6. Okay, now 6 is neither a multiple nor an integer power of 10. So in exact terms, okay, the base 10 logarithm of 6 is already simplified. And as for the subsequent terms, okay, we just have to convert the exponents to coefficients. So we're going to have the base 10 logarithm of 6 and a half plus 2 times, okay, the base 10 logarithm of all of x plus 5 and I have minus, okay, 4/3 the base 10 logarithm of x. And just taking what we have now. Okay, so in 8, we're looking at squeezing together, okay, these base 2 logarithmic terms and making into one expression. So what I will do here, okay, so we have from the start, okay, so looking at writing as a single logarithm, okay, so any coefficients I have, I can express as powers. Okay, so we have looks like the base 2 logarithm of w to the third, and we have minus, okay, the base 2 logarithm of y to the 1/5, and we have plus the base 2 logarithm of x to the 4th, and looking at putting together. Okay, so I got the coefficients converted, and just compiling together. Okay, so w to the third stems from a positive logarithmic term, so that's going to go at the top. Y to the 5th comes from a negative, so this will be situated on the bottom. And we have plus base 2 logarithm of x to the 4th, so x to the 4th will go on the top. So this will be your answer, and if there could be any other way to express this, this would be like taking the base 2 logarithm of w cubed times x to the 4th, and y to the 1/5, this will just be the 5th root of y. Okay. All right, and now just for what we have in the case of number 9, okay, we got this time a logarithmic equation. And again, when we looked at exponential equations or looking at reducing logarithmic terms, I took the base a logarithm of a to the x is equal to x. Now for logarithmic equations, okay, now the close relative of base a logarithm of a to the x is a to the base a log of x is equal to x. And we have, in the case of number 9, okay, so we got the base 9 logarithm of x is equal to -2. And if I take care of the base 9 log appearance, I can treat both sides as powers, to which the exponential base 9 is going to be raised. So we have 9 to the base 9 logarithm of x is going to be equal to 9 to the -2. So the left hand side becomes x. X is equal to 9 to the -2. And it says to simplify your answer as much as possible. And what that would mean, okay, we have for 9 to the -2, this would be the reciprocal of 9 to the 2nd. And 9 to the 2nd is 81. So 9 to the -2 is going to be 1/81. And that'll be your simplified result in this case. All right, and then we have just taking what we have now for number 10. Okay, and we have a similar type of scenario. And here we have the base 4 logarithm of the quantity of 3x minus 8 is equal to 1. And using this property, so now it is going to be the exponential base 4 that we're going to use, treating both sides of this equation as powers. Okay, so left-hand side becomes 3x minus 8. And the right-hand side, okay, 4 to the first, that is going to be at 4. And so we have a two-step linear equation. And if I add 8 to both sides, okay, so we're going to have 3x is equal to 12. And we'll have the x's equal to 4. And let me just mention, if I get too far ahead, okay, so from this one, okay, x had to be positive. And likewise, 3x minus 8, that had to be positive as well. Okay, and with x at 4, 3 times 4 is 12 minus 8 is 4, so 3x minus 8 was definitely positive. And I'm going to go ahead and squeeze in number 11. Okay. And for this one, okay, so we got negative 6 times the base 4 logarithm of 5x is equal to negative 12. And you can make life simpler, and one might pose the question, can you divide this whole equation by the coefficient that is in front of the logarithmic factor? In this case, yes. Okay, so if I divide out, I'm going to have that the base 4 logarithm of 5x is equal to 2. And once again, we have for applying the exponential base 4, just to take care of the base 4 logarithmic appearance. So the left-hand side is going to be at 5x. And we have that 5x is equal to 16. And with division by 5, we have that x is equal to 16/5, which you can also write as a decimal at 3.2. And again, 5 times 3.2 is 16, so 16 is a positive value. Okay, so we do have x to be at 3.2 as the solution.